So let's say you take an object that you have to measure, and let's say as a group, what are the steps that you have to take? All right. So then think of like this. Object that I'm going to give you here is going to be a cylinder. That's right. So let's say cylinder. And then you're going to, as a group, you're going to do some measurements. Well, the measurements that you can do, for example, can be the measurements for the diameter of the cylinder, which is this portion, or it can be measurements for the length of the cylinder, which is, let's say, this portion. All right, that means you can measure the diameter and you can measure the length. But the way we approach this experimental result, right? So because what I want as a group for you to give me here is the diameter and then the length. But you don't just, let's say, as a group of 4, for example, you don't just measure it once and then come and tell me, okay, so this is what we measure. That's not how it works in an experimental lab. Doesn't matter if it's a physics lab, biology, chemistry, and things like that, right? Or some kind of engineering. So the idea here is for a actual measurement. Well, let's say you have one person measures and this is 6.2 centimeters. So before actually bringing this measurement to me and saying, okay, so we got the diameter and this is 1.62, well, you want to verify that. You want to verify that by having maybe someone else measure the same thing. That means what you need to do here, if you have an object that you're measuring and you are able to measure this object once and then measure it again and again and again, that means this is some kind of measurement with, let's say a tool that is provided. Then what you can do here is you can, let's say, get a measuring or measurement data set. Okay, data set. And the data set usually has 5 to 10, on average, in the experimental labs that we would have done, 5 to 10 measurements. And we call them trials. Which means that if we have a one person measuring, then you would just call that one of the measurements, one of the trials, and then give the cylinder to a second person and have the second person measure, and then the third person, and then the fourth person, let's say, and so on and so forth. That means every person measures, and when the person measures, in a way, you also verify the previous measurement. Is it correct? Is it reliable? Now, one of the things I've seen in, for example, experimental labs is this. So let's say I have a group of 5, let's say, and then they bring me a data set that is like this. All right. So let me tell you this. This almost never happens. All right. So this almost never happens when you have 5 measurements by 5 different people of something and you get exactly same thing 5 times. What it means is that they measured it once and they just copied the answer 5 times, 4 times, and then you have this data set. That's not how it works in the experimental lab. And the reason it doesn't work like that, because in any experiment, we have errors, okay? That means any experiment involves errors. And errors come in 2 different types. We have random errors, and there are systematic errors. Okay. So the random errors are systematic errors, always part of any experiment that you do. So what we can do here is then, when you're doing an experiment, you want to take into account these errors. Some of these errors can actually be avoided. And one way, for example, we can avoid these systematic errors is by calibrating the equipment. Because systematic errors is the problem, let's say from your systems, problem with your device, problem with your, let's say, the setup and things like that. And you can change the setup. You can make sure that, for example, if you need a flat surface, you can make sure that surface is flat. You can, use the tools, right, to make sure that surface is flat. Because if there's a little bit of incline, then the object can actually slide down instead of just sitting there. So we can more or less eliminate this by calibrating the equipment before starting the experiment. random errors you cannot avoid because these are human-made errors. These are human-made errors, and human-made errors always unpredictable. You know, you don't know, let's say, what is the reaction time for one person compared to another. Imagine a simple experiment. So as a group, you have to take an object, let's say a tennis ball, and you have to drop that from 1 meter from the ground. So you have to drop it and measure the time it takes to hit for that ball to hit the ground. So you can see, right, it requires you to use a stopwatch, for example. So the stopwatch works like this. So you release the ball, then you start the timer. And then when it hits the ground, you have to stop the timer. And you can see, right, sometimes there could be one person who has, you know, good reaction, let's say, good reflexes. So release and start and hits the ground and stop is, let's say, something that easy for him or her, right? And then they can do that very precisely. But then maybe another person, releases and then starts the timer, or hits the ball, hit the ground and then stops the timer, which means then you're going to get few extra seconds or milliseconds, but that's already something that is going to be different, which means then whenever we're doing experiments, we're always going to expect some numbers to be different. That means the measurements, right, will be not necessarily like really off from one another, but at least a little bit of, there's a little of, errors. But again, errors doesn't mean that it's wrong. It just means that it's a little bit of deviation between the data points. All right, so now, again, this does not mean that you have a bad data set or something like that. This is expected. Any experimental lab has this random errors where when you're measuring something by 4 or 5 people, you're gonna get some, little bit of deviation. But then the question is this, as a group, what do you do? So you have a data set with 5 data points. How do you, represent your measurement? Well, there are some mathematical tools we can use to do that. And one of them, let's say, would be to find the average of your data set, of your measurement. And the equation for average, and this is a general equation, so let's say for some quantity X that you're measuring, so average represented with X bar, and this average calculated actually, and it's not a measurement, it's a calculated quantity. But you can calculate if you have a data set using this equation 1. So this will be X1 plus X2 plus ... plus Xn. N is the number of measurements. And then this is divided by number of measurements. Okay. So this will be then, for example, let's say best value that you can use to present the diameter of that cylinder. Not actually your data points, but the calculated average will be, let's say, the best data point or best possible value for your diameter. So for example, for the diameter, I put D bar, right? This will be, let's say, D1 plus D2 plus D3 plus D4 plus D5. This is divided by 5 because I have 5 measurements. All right, so now I'm gonna, again, I'm not gonna calculate this. I'm just gonna make up some numbers. But again, if I add all of those values together and divide by 5, I'm gonna get some number that basically is average of those numbers. So let's say that number is 1.635. Again, so I'm just making up that number, but let's say it's 1.365 centimeters. Now, one thing I'm gonna do, and this is something I expect from you guys also, is this.
That's actually really close to the real answer.
Oh, really?
Yeah, I calculated it.
Awesome, so that's good. All right, so here's what I have. Notice how many decimal points I have for my data set. How many data points do I have? Decimal points. Or how many sig figs and
3 significant figures.
3 significant figures, and how many decimal points?
3
2
points.
2 decimal points and 3 sig figs. Yes. Now, what we do here is this. Remember, the average is not a data point, right? Average is something that we calculate from the data points. So technically, it's more precise. So then what we do, we include 1 extra decimal point. That means you have to have extra decimal point for the average.
Is there
always.
a specific number of extras, or is it just a single one?
just one extra, just one extra. So one extra decimal point. Because everything else is going to be, you know, way beyond the precision of, you know, let's say your measurement. But one extra decimal point shows me that this value is average of your data set. That's how I know that this is the average.
Can I ask a quick question?
Mm-hmm.
So let's say if it was like an exam question and it says, calculate the average, for example, is it assumed that every answer that we input as our own has to be in significant figures, or unless it's specified, then we'll do significant figures?
Well, think of it like this. So generally, for example, when you do mastering physics homework, something like that, they actually, mastering physics platform is very sensitive to the sig figs. So that's why I'm trying to teach you guys to pay attention to those like sig figs and things like that. Because this handout teaches you most of the information that you need about sig figs. You will be able to find everything that you need about sig figs in this handout. I don't go over that because most of you probably already know that, or you can just review from the handout. But for example, if you if you're multiplying 3.52 times 5.2, how many sig figs should I have in the answer?
2.
2, because you go with the least amount of sig figs overall, right? But for example, if you have 3.52 plus 5.2, is it also goes in terms of 2 sig figs?
No, it goes by the decimal place.
Exactly, it goes by decimal place. So for example, here I will get what? What will I get? So 8.72, right? So let's say this is the answer, but I'm not going to be keeping this, because what I have here is I have to look at decimal points, 1 decimal point, 2 decimal point. So my answer should have just 1 decimal point, and that's the answer now. So that's why those are the things, basic stuff that you probably learn in, I don't know, pre-algebra or something like that. Those are the things I expect you guys to know. And I have a review for you on the handout. But the idea here is that this is not something you probably have seen, right? Average, let's say sig figs for the average is not something they teach you in those classes. So that's why I want to make sure that you guys know every time you're calculating average of any data point or data set, include 1 extra sig fig. And this is mainly for the labs. Whenever you're calculating the lab, right? The average and, let's say you need to include that 1 extra decimal point. All right, so then the second thing that you need to do, using the mathematical tools is this. We have errors, right, involved in our measurement, as I mentioned, human-made errors, and we have to show those. And we can already see that every data point is slightly different from the average. So then what we do here is we calculate what we call uncertainty, which is basically, we use this term in physics, but there's also in, let's say, in math, this is known as standard deviation. Same thing, standard deviation. Or in physics, we just use uncertainty. I'm going to always refer to this as uncertainty, which is basically how reliable your data set is, basically how close the values are to the average and things like that. And we use Greek sigma for that, so sigma of x, right? It's a quantity x. And the equation is this. Take your first data point and find the difference relative to the average, square that, plus the second data point minus average, square, then plus that, then your nth measurement minus the average, square. Then this is divided by n minus 1, and on top of that, the whole thing is inside the square root. Right, so we have this equation, basically. All right. So which means I can then do the same thing with diameter, right? So I can calculate sigma for the diameter, which basically will be the same, plug in each data point minus average square plus the second one minus average square and that. So I calculate the value. And we have another sig fig rule. This is for the uncertainty. And this is a little bit simpler because this is what you have to do. always just one sig figure. That means your answer should have only one significant figure. That's it. Maybe your calculator can give you 5, 10, but you just round it to just one sig fig. So let's say in this case, I might have 0.02 centimeters, and that's it. It could have been 0.2145 or maybe 0.018, something, right? But I rounded to just one sig fig. So this is what I'm going to be checking when you submit your lab report for this lab 1. I'm going to be checking, do you have average calculation? Do you have uncertainty? Are they in correct units? Do they have, this correct sig figs and things like that? So make sure you guys following all of those things. Because here's then what we can do. As a group now, you are ready to present your data for the, or your measurement for the diameter. Because if you are asked to find a diameter of the cylinder to scientifically, to accurately, as an experiment, right? Experimental measurement, to present your data, you have to come and tell me, all right, so we measured it and we figured out that the best value of the cylinder that we can have is the average value. But because of the random errors involved in the measurement, so technically there is a possibility that this number could have been as high as the uncertainty of that, or as low as the uncertainty of that. That means what we have is this, it's 1.635 plus minus 0.02 centimeters. And you will see every time you actually looking some kind of, let's say real life research paper or something like that, when they give you information about their measurement, they will always have it like this. They will always have let's say the possible value that they might have, but plus minus the uncertainty, because any measurement, does come with uncertainty. Doesn't matter what it is, right? Anything comes with uncertainty, right? So let me give you actually a real life example. For example, right now, if you're following the presidential elections, right? Trump versus Biden. So you probably heard of, they're always using these numbers. Okay, so let's say, all right, so the Biden is 49%, Trump is 42% or something like that. But you probably also hear them saying that, well, it can be plus minus, let's say 2%, right? At least, they say it's 49, but there is a plus minus, 2% always uncertainty. That means this number technically can be as high as 51 or as low as 47. Same thing is here. Maybe this has an uncertainty of 3. So it can be 45 or it can be, let's say, 39. That means anything that you actually measure, comes with uncertainties. Same thing is here. If you're talking about the diameter, what you're saying here is this. So let's say this distribution is for my measurements. That means kind of like my measurements spread out like this. Well, the average represents, let's say, the peak of your graph, which is the average. But then you have plus uncertainty, which is maybe somewhere over here, or minus uncertainty, somewhere over there. That means any experimental lab, best way to present your data is to give possible range of measurements, okay? Because there is no such thing as 100% value of something, all right? What you measure as 1.635, maybe another group will measure as 1.645. Again, because that number, can fluctuate depending on the errors involved in the taking data. That means here's the diameter. So we got average plus minus uncertainty. And let's say you get same thing for the length. Exactly same steps we can take for the length. Measure it 5-6 times as a data set. Then use the equation 1, calculate average. Then use the equation 2 to calculate uncertainty and present it like this. So maybe, for example, this will be 1.635 plus minus 0.02 centimeters that I had. This is maybe, 6.352 plus minus 0.05 centimeters. There you go. That means this is how I expect to get the result for those measurements. Because you have to give me your best possible value, but you have to also show me that, there are errors involved in your measurements, so you take those into account as well.
So the uncertainty is like a margin for error?
Not necessarily, not necessarily. Uncertainty is how reliable your data is, basically, how reliable your data set is, okay? Because margin of error is different thing. For example, margin of error goes like this. Remember, this is measured, right? This is measured. This is what you measure as a group in class. But maybe when the department received those cylinders that we can use in the labs, we also had the diameter value from the manufacturer. So let's say I'm going to call this accepted value. That means they measured the diameter as soon as they made that. As soon as the diameter was made, you know, they measured diameter, let's say, and they send me that information. But still, even those manufactured, when they measure, they would still give me in terms of uncertainty and let's say this is accepted average, right? And uncertainty for that. So again, so this is the measured, and now this is the, let's say the accepted or theoretical, right, value for the diameter. Because one thing we can do from here is this. All right, so you bring me your measurements, and as an instructor, I want to go over and look at to see if you have accurate measurement. That means, is your measurement accurate or not? Well, to verify if it's accurate or not, I need to compare it to something, right? And what I do is compare it to this accepted measurement value. But you know, for the accuracy, then what I need to do here is I need to then look at what we call error in your measurement. Error in your measurement is defined as the difference between accepted and measured, for example, averages. Okay, so but let's say what we have here is this. For example, the accepted here is this. It's 1.650 plus minus 0.01 centimeters. That means what I have here is this. This is accepted. This is your measured. And the question here is this. Is it accurate or not? What do you guys think?
It's pretty close.
Close, but it's off by the last 2 digits.
Well, it is close, but that's not what we do in let's say in a laboratories, right? We don't just look at two numbers and say, okay, they're close, so that means it's probably a good experiment. No, what we do, we verify that, you know, accuracy by calculating. For example, we start with the error, which is basically 1.650 minus 1.635. And we get a number which is basically an error in your measurements. All right, so I get this 0.015, for example. All right, so that means this is your error. And error, again, error doesn't mean that it's a bad experiment or it's a mistake or something. It just means that this is the difference between measured and accepted, let's say, averages. But this number doesn't, even this number doesn't really tell you much. It doesn't tell you if it's a, you know, good experiment or not. So then one thing we can do to actually visually have a, you know, better understanding of the experiment or experimental accuracy, we calculate what we call percent relative error, which is basically error divided by accepted average, right? So just, you know, accepted average, then times 100%. So that's why it's a percent relative error. Then I take error, which is 0.015 centimeters, divided by average of the accepted, which is 1.650 centimeters. You can see the units cancel out. Then multiply this by 100%. So let's do that. 0.015 divided by 1.650. Then this is times 100. I get this, 0.9 or roughly 1%. So now, what do you guys think? Is it good experiment if your percent error is 1%?
Yes, as long as it's lower than 5%, right?
Well, actually, that's a good point. Not necessarily. So think like this: to know if your margin, if your percent error is good or bad, you need to know the margin of error of this experiment. So let's say in my lab, I would probably give you guys 5% or maybe even 10%. So 5% or 10%. So not necessarily just 5%. There are labs that is 10%. There are
So it's
labs
just
that
a
may be,
given?
let's say, 2%. So, but still, this is a good experiment if this is the margin of error for my lab.
So what you're saying is the margin of error is something that you'll give us for the lab?
I might give you that, yes. For example,
Oh,
if you
okay.
get 30%, right, and my margin of error is 5, that means, you know, I take 5 to be margin of error because of the accuracy of the experiment that I think you should get, right? So when you get 30, that means you just didn't take accurate measurements. You weren't careful.
Okay.
You were rushing through the experiment or something like that. All right, so that's kind of what I have. That means most of the time, I am expecting under 10%. This is my margin for all, you know, standard for the labs, okay? Some labs that can be a little bit higher, for some labs that can be a little bit, you know, lower, depending on if I think the, you know, experiment itself can be, you know, taken much more accurately. That means if you are the one who measuring the time for the object to go and hit the ground, I'll probably make it a tough 10%. Because there are going to be a lot of, you know, errors involved. But if you know, the object is being dropped from some height and then the time is measured by a computer, by a photo gate, then that measurement of the time is extremely accurate, then I might actually use 5%. That means the only error that can come from this experiment is how well you measure the distance from the ground. Because time has almost no error involved because it's a photo gate. Well, very, very little error involved because the photo gate is a computer does it everything extremely accurately. All right, so that's basically how you would find the percent error.
I have a question.
Go ahead.
Where do you, is the accepted number, is that a given? Where it says in your diameter?
Most of the time it will be, yes. Most of the time it will be given. For example, let's say there's an experiment when you drop an object, right, and measure the time, and that experiment generally involves to find this quantity that we call acceleration due to gravity. So this g, lowercase g, and this has a number of 9.8 meter per second square, something we're going to study next chapter actually. So let's say this is well-known, you know, volume. G is equal to 9.8 meter per second square. That means objects accelerate using, you know, let's say due to free fall at this rate. That means this will be then accepted value. And then when you do an experiment, and let's say you find your own experimental gravitational acceleration, maybe let's say you get 10.5 meter per second square, then you will take this measurement and compare to the accepted value, that is 9.8. But
oh, I see something. The accepted value means kind of like the, it's already kind of a fact or like a theory that's established.
Exactly. Because most of the things what we do in labs, we verify something that is, you know, already established. Yes. Unfortunately, we are not finding anything new in these labs, you know, but we will be, you know, verifying some of the, you know, known facts, known given constants and things like that. Definitely.
I see. Okay, thank you.
All right, sure. All right, so then here's what I have. Again, if I have given you this cylinder, then you can remember, use this equation 1 for the average, which is x1 plus x2 plus ... divided by n, and equation 2 for the uncertainty, which is square root of x1 minus x average square plus x2 minus x average square, and plus ... This is divided by n minus 1. So if you have basically some type of measurement, the quantity that you're giving me that can be put in a data set, which means you can repeatedly measure it, have a 4 or 5 measurements and put it in a data set, then you can use those two equations to give me the diameter, for example, right, in terms of its average and uncertainty, and let's say length in terms of its average and uncertainty. So this type of data set can use equations 1 and 2. But there could also be other type of things that I can ask, other quantities that I can ask, that could be, you know, a little bit different way that you need to do the data analysis. For example, my next thing that I want you to, let's say, give me is the volume. how would you measure the volume of the cylinder, for example? Remember, technically what I'm giving you is some kind of ruler, nothing else.
Are you
Can
asking
you,
for the equation for volume of a cylinder?
well, in a way, yes. That means, you know, if you have an equation, which means that there is a way of actually calculating the volume. So, but right now, using this tool, we can't measure the volume directly. You cannot, let's say, take the ruler and measure volume directly 1 time, 2nd time, 3rd time, 10th time, right? And have a data set. But there's an equation. Anybody can help me with the equation for the volume?
Is
Pi r
it mass
squared
over
H.
density?
No, we're not using that equation.
Cylinder is
1/2 times base times height.
It's the
Pi
area
r
of the
squared
circle multiplied through the height.
It's pi r squared
times
height, no?
length or height.
times length. In our case, it's length, right? So I'm using L instead of H. So yes, this is the equation. Because what we have here is, so let's say we understand that half of the diameter is what radius is. So let's say then we can replace radius with half of the diameter. And then basically we have this equation for volume. Pi over 4, because 1/2 is squared, so pi over 4 times diameter squared times length. So this is my equation that I can use to find volume. But that means what we're doing here is this. We're not measuring volume. We're calculating volume. We are deriving volume. And we are deriving using, you can see, right, using the diameter and length, using 2 things that we already measured. But volume is not something we can measure, but again, we can derive that. So you can see, right? So this is sort of like a different type of quantity.
Can you
It's not
measure,
something we measure, something we calculate.
can you measure volume without deriving it from?
Yes, we can, but we're gonna learn about that in chapter 13.
Okay.
It's actually, if you want to get ahead and look it up, it's using Archimedes principle. Okay.
Yeah, sure.
All right, but let's say with the tool that I give you, you cannot do that. So now, what do you guys think? When I want to calculate the value for the volume, which diameter or length value should I use?
The average?
Remember, I had a data set, right, for all of them. But if you want to calculate the volume, won't you want to, like, let's say, use the best value that you have for those, measurements?
That would be the average, right?
Exactly. That
Yeah.
will be the average. Exactly. So that will be the average. That means in this equation, if you use the average diameter and average length, you are technically calculating average volume. Because here's the thing, even if the volume is something you are deriving rather than measuring, I still expect this. I still expect you to give me volume in terms of its average and uncertainty. Because if I'm asking you in the experimental lab to give me volume, I expect average and uncertainty. And this is how you find the average. At least, in terms of average, is pretty straightforward. You can do that, using this equation. But the question here is this. How about this guy? Do you guys think I can use this equation too to find the uncertainty in volume?
Yes.
Well,
I don't think so because you're not physically doing the experiment.
okay, so the second answer is closer to the right answer, but not, in a way, yes, we're not physically doing the experiment, but when we're not physically doing the experiment, it means what? It means what don't we have?
You don't have data points to average.
Exactly. We don't have a data set. We don't have a data points to use. How many values of a volume do I have right now? Like
Just
how
the
many
one.
data
Only one.
points?
Equation can sit out.
Only one, right? I have just only one value. That means I have only one data point. Look at this equation. It's n minus 1. If my n is 1, that equation won't work, right? It's 1 minus 1 is 0, just basically undefined. That means this, that's why I said, right, equation 1 and 2, specifically for the data set, something you physically measuring, getting data. Volume, we're not physically measuring. We're not getting a data set. We have only one data point, so we cannot use that. But it doesn't mean that we can't do anything about that. So this handout also teaches us a technique that we can use to calculate that. So this is known as a propagation of error method. So propagation of error method, which is, again, it's a technique that, you know, template equation that we can use to find that. But again, this assumes one thing. This assumes that you already have this information. You already have the average and uncertainty of the diameter and average and uncertainty of the length. That's why you can use that to find the volume average, right? The question here is this propagation of error allows us to find the uncertainty of derived quantities, like volume. Let me give you another example, which we'll be using in the actual, you know, in a handout. So let's say I have a sheet of paper like this. So, well, I didn't want to make a square, so let me make it a rectangle. Okay. Well, all right. So what can I measure about this rectangle? It's not a square; it's a rectangle. Let's say.
The length,
The length and the width.
Exactly. I can measure the length and I can measure the width. So can I then use equation 1 and 2 to find their uncertainties and average?
Yes.
yes.
Yeah, because it's a physical measurement, then I can find average and uncertainty for length, and I can find average and uncertainty of the width, right?
Professor, if on one of your measurements for the data set, you had an error that's like unaccounted for, when do you know to omit a point of data just so that it doesn't completely like throw your average outside of the standard deviation?
Yeah, it's a good question. So let me give you an example in terms of the data set I already have. So for example, you can see here, right? All of them are 1.6 something, right? And let's say this one is 4.6 something.
Okay, yeah.
Probably obvious, right? That this is probably just something, you know, weird happened there. So you
What
can
if it
just
was off
ignore
in
it
the
and
10th?
measure it again.
What if it was only off in the 10th place though? Is that enough to consider that omissible?
So let's say, which is what? Let's say a 7.1?
1.71, yeah.
Well, I would say you keep that because it's still
Okay.
close enough.
Okay.
That you keep. But if it's, let's say it's really off, then you can omit that.
So is there a standard rule or is it more of a judgment call?
I would say if it's within 20% of other measurements, you keep it. All right, so we were here. So length and the width. What else can you give me about this rectangle? What other thing you can give me about rectangle?
Degrees and
Area.
angles.
Not degrees. What do you mean
Don't we
degrees?
know that's 90.
Area?
I agree with area.
Area. Exactly, area. And I heard another thing which was correct.
Perimeter.
Perimeter, yes. Also perimeter. Are those things measured quantities or derived quantities?
Measured.
How would you measure area?
Area is derived. Perimeter can be measured, but you can also derive it. So
Okay, how would you measure the area? How would you measure the perimeter?
area is length times width, and the perimeter, we just measure the sides and add them up.
Again, but you're not measuring it, right?
You're deriving it.
You're deriving it. See, the area is length times width. Perimeter is 2 times length plus 2 times width. See, I mean, you're not really measuring perimeter. You're just calculating it, right? So that means it's a derived quantity. That means, for example, those two things are derived quantities, just like the volume. But there's a little bit of difference between those two things. Who can tell me what is the difference between how we find area, how we find parameter?
Could you explain
measured
one more
quantity.
time why perimeter is not measured, it's derived? Because even though we have that equation, I don't understand how we're not just measuring and adding up the sides.
Well, then why would you not say then area is also measured? All you're doing is multiplying the length and width, right?
Because we know that multiplying is a different function than addition.
No, by deriving, I mean you are using other things to find this quantity. Okay. And we are, right? We are using length and width to find the perimeter. Without length and width, you can never find perimeter. But without perimeter, I can find measures length and width, right? Okay. So look at the structure of the equations. What is the difference between them?
One of them you're adding, one of them you're multiplying.
Exactly. And that's a big difference. One of them is, you know, basically product, right? You multiply or divide. That's one type of, you know, calculation. The other one is adding or subtracting. That's another type of calculation. And that's why this propagation error comes in two types. One is for that, you multiply or divide. Okay, so basically product or division. The other one, let's call this B, this is for sum and difference. Okay, you divide or, you know, oh, not, sorry, you the difference, or let's say you add them together. So that's why, let me show you the equation format. So, and for this is a template basically, and we are using dummy variable for that. So let's say the Z here is a dummy variable. So the Z is some kind of quantity that we are deriving, right? So basically it means nothing, just a dummy variable. It is technically then can be a product of three measured quantities, and those three are measured quantities, some kind of measured quantities, right? That means we expect X is some kind of measured quantities that can be, you know, come in with its average and uncertainty, same with Y, and same with the W. That means those things are measurements. Those are measurements. But equations, some equation can also have what we call a constant. So A is some kind of constant. All right. And another thing we can have is that some of those quantities in the equation can have exponents. For example, X can have exponent, Y can have exponent, and W can have exponent. So these quantities, right? Let's say B, C, and D are exponents of these measured quantities. So then this method tells you that if you have an equation that have this format, then you have template equation to calculate uncertainty of this quantity that you're deriving, which is basically uncertainty of that quantity Z. And the equation is a template which goes like sigma Z over Z squared equals then B squared sigma X over X squared plus C squared sigma Y over Y squared plus then a D squared, then sigma W over W squared. Again, this W here is not the width, it's just dummy variable W. Okay. It tells you that if your equation has this format of A, then use A star to find the uncertainty of that quantity. All right, uncertainty of that quantity. Now let's look at this then. So we have here is a volume, which was average volume was then pi over 4 times diameter average squared times length average. And we have another equation. For example, area was length times width. And obviously, you know, we use averages. And then we have parameter, where it was 2 times length average plus 2 times the width average. So now let's look at those three equations. Which of these equations is type A?
Area
Area.
and volume.
and the volume. How about the parameter?
No.
No, because it's not a product.
Exactly, it's not. Because then there is a type B, which tells you if you calculate some quantity Z, then it could be the sum of some measurements. Okay, it's X plus Y plus W. You're summing those, measurements, let's say. Remember, those are basically the X, Y, and W are measurements. And one thing you can have here, you can also have coefficients, A, B, and C. That means what we have here is this. So X, again, is some kind of measurement. Y is some kind of measurement. And W is some kind of measurement. In this case, though, then A, B, and C are just some coefficients, constant, right? So coefficients, let's say. So that's why, for example, then parameter, which is 2 times length plus 2 times width, is type B rather than type A, because this is nothing but, two, average values added together, which is like X and Y here, right? To get the unknown, which is the derived quantity parameter. Okay. So then B comes with its own uncertainty equation to find the uncertainty Z squared. So this goes like A squared times uncertainty in X squared, which is uncertainty in your first measurement square, plus B squared times uncertainty in your second measurement square, then plus C squared times uncertainty in your third measurement square. So those go together. So like, let's say, there you go. All right, so now I'm going to give you an example for the type A. And we agreed, right? Volume is type A, right? So now,
Yes.
that means I can apply type A and A star, basically A and A star, to find the uncertainty in volume, because I already have this. Remember, the idea here is this, that I already have diameter in terms of its average and uncertainty, and I already have the length in terms of its average and uncertainty, and I use them to find the average of the volume. But what I need right now is to find uncertainty in the volume. That's one thing that I couldn't use using equation 1 and 2. So I needed a new technique, which is this particular technique, to find that. So let's do that then. What you do here is this. So this is your Z equation, AX, BY, C, W, D. And then use your volume equation. Average volume equals pi over 4 times diameter average square times length average. So what you do here is simply looking at each equation and then directly, comparing each term. Remember, this Z is something that you are deriving. What would be that equivalent of that in our equation of the volume?
The average.
V average, exactly. It will be V average. Why? Because, well, what we're deriving in this equation is the average volume. Next will be A. A is some kind of constant in your equation. What is a constant in my equation of the volume?
Pi over 4.
Exactly, it's pi over 4. Because pi over 4 is just a number, right? It's a constant, it doesn't change. It's not a measurement. So pi over 4 is what we have for A. Then we continue, right? So I have X, and X is my first measurement. So what is my first measurement in my equation for volume?
Diameter.
Diameter.
Diameter. So I put like average
Diameter.
diameter, right? Yes, average diameter. Then B would be an exponent of that guy. What is the exponent of the diameter?
2.
Squared.
It's 2. Then Y is my second measurement. So Y would be what?
Length.
Average length. And then C would be its exponent. So what is the exponent of length?
1.
Exactly. It's technically 1. Yes. How about W and D?
We don't have it.
You don't have it?
Our equation doesn't have it, so you can just ignore it. All right, so that means when you come to this template equation, all you have to do here is this then. Look at the template equation. You take where you have z, well, replace z with the average volume. That means if I come to this equation, see over here, this becomes basically, average volume. And this becomes average volume, right? So basically anything that is z becomes volume. All right, so let me actually, do that calculation here. Or like, let me show you here. So what we do is this. So sigma, instead of sigma z over z, becomes sigma v over v average squared. Then here I have b squared. Then I come back and I can see, all right, so for my equation, b was 2, so it becomes 4. Then I have sigma x over x squared. Well, for me, x is the diameter. That means it becomes uncertainty of diameter over diameter average squared. Then plus, then I have c squared. Well, for my c is 1, so I can just leave it like that. And then I have sigma y over y average squared. Well, y for me is the length. So this becomes sigma length over length average squared. And that's my equation for the uncertainty in volume. Because remember, what I have from this equation is this. Uncertainty the diameter and average diameter, I already have it. Remember, it's here. Uncertainty in length and average length, I have it. And even average volume, I have it. The only thing I don't have in this equation is an uncertainty in volume. And that's what we do. We take the square root of both sides, and then I write sigma v over v average equals square root of all of those things inside the square root. I can remove them. And then, but after that, what I do here is I just move this volume average to the other side and multiply to that, square root. And this will be how I calculate the uncertainty in volume. All right, so again, you can see, right, it's a much more involved process, but we're gonna have to do that because volume is a derived quantity and we have one data point, and the only way to find its uncertainty is using this propagation of error technique. All right, any questions on that? All right, so then you're gonna use this in your lab 1. So you're gonna have to use this technique, propagation of error technique in your lab 1.
Where'd you get the 4 when you square rooted the whole thing?
Where did I get the 4?
Yeah.
Well, the 4 is from here. See, the b equation has a b square, right?
Mm.
And b is the exponent of the diameter, which was 2. So 2 squared is 4.
Oh, okay.
Could you point out to me which letters are the constant and the derived?
Well, the only one that we have here derived is the volume or the z. Z, that's why z and volume are identical in a way that they are derived quantities. X, Y, W are measured quantities, like I have it over here.
Quick question. So derived would be anything that its components can be measured.
Well, derived is what I call derived is something that you can use measured quantities to calculate.
Okay.
I have some measured things already, and I can use them to find this quantity, derived quantity. I can add them together, I can multiply them together, I can divide them, those measured quantities. That means when I add, divide, subtract, right, multiply the measured quantities, then I am getting this derived quantity.
Okay, thank you.
Sure. All right, so we're still not done. I have one more thing to go over and then we'll be done. But this is basically another type of data that we have to deal with. So well, you can say, like, let's say direct measurement is one type of data. Derived quantities is another type of data. And this one is type of data where you are pretty much doing an experiment where when you change one thing, another quantity changes. For example, let me kind of explain it like this. So let's say you have a spring. Okay, so you have a spring. See, this is the position of the spring. So I'm going to call this x0. This is the position of the spring where nothing is acting on the spring. But let's say then what I do here is I, put some black on it. So I put the black. Well, what the black does, it's, it pushes on the spring, right? Black has a mass and it pushes on the spring. Well, when it does, the spring is actually compresses. So let's say it compresses to this distance. That means what I have here is this distance here, right? This distance that the spring compresses, by how much it compresses, depends on how much, let's say, weight this block has. Well, think like this. If I continue adding more weight, right? So let's say, this is its equilibrium. If I add more weight, then it will compress even more. So imagine if I have more weight, then it will compress even more. That means here I have x1, then maybe here I have x2, right? That means more weight I put on the spring, more it will be compressed, right? So it's easy to visualize, right? So you have a spring, more stuff you put on it, more it will be compressed, because how much it will compress, this displacement, right, depends on how much weight I have. So that's why what we do here is we take a type of data that basically goes like this. So here's going to be, well, how much weight we have. Weight is actually, example of what we call force. We're going to talk about that in a little bit, but let's say this is an example of what we call force. All right, so, and let's say when there is no force, it's basically no displacement. The spring is just sitting there. Then my x will be 0. But then, for example, I'm just giving you an example, right? So, like, for example, when I do 10 amount of force, then maybe this one goes, let's say 1 centimeter displacement. When my force is increased to 20, well, this is also increased to 2. That means now it's 2 centimeters stretched or compressed. When this is 30, this is then 3, right? And so on and so forth. That means what I have here is I have a data set where by changing one parameter, right, one quantity, you are automatically changing another one. All right, so that's why this is a little bit different. So you have two things affected by one another. The best way then to describe this, we can see then the force, you can see, right? This is 0, this is 0. This is 10 times bigger. This is 1, in a way, let's say, or let me do it like this. Probably it's easier just for the sake of proportionality, right? This is 10, the other one is 10. This is 20, the other one 20. This is 30, the other one 30. So what can you say about how F and X are related? What can you say about how they're related?
They have a 1-to-1 ratio.
Yes, so they are linear proportional. So let's say in this case, 1-to-1 is a little bit, ideal, right? Perfect case scenario. But the idea is that they are directly proportional. When I increase this, the other one increases. When I increase even more, the other one increases even more. That means they are directly, right, linearly proportional. Now, generally, when you go and change the proportionality sign to equal sign, you always introduce some kind of constant. And that constant here is K. So it's K times X. This K is known as a spring constant. So spring constant, all right? It's a spring constant, which is information about how stiff the spring is. And for example, in this particular lab, I want to know what that spring constant is. I want you to give me the value of K. Let's say, what is K? But it's an experimental lab. That means you need to give me average K and its uncertainty. I want it like this. All right. So the question is, how do we get this data that we have, data set of the force and displacement, right? How do we get this data so that we can find the K and uncertainty in K? And this is the equation that relates, right, all of those quantities. Well, here's what I have. You can see, right, this is force equals K times X. What we do here is we use the graph. We use a graph to do that. Generally, this is the best way to use, to go around and, do this type of data calculation using the graph. Because then I can use this y equals m times x function. You guys know, right? Y equals mx. Y is the quantity on the y-axis, is the quantity on the x-axis. M is the slope of the line between them. In this case, if I'm plotting force on the y-axis and distance on the x-axis, what I get is basically this. All right, so this is the force, let's say in newtons. This is the x, let's say in centimeters. And I use the data to plot the data points. So these are the data points. So I put the data points, and you're gonna do this by hand using the graphing paper that I provided. All right, so the force. So what you need to do, you also need a title. By the way, the title for this one, we're gonna learn about this equation. This equation is known actually Hooke's law. This is Hooke's law. All right, so then things like this. I use the table to plot the data points. And then what you do here is you take a ruler and then draw a best fit line that goes through most of your data points. See, I have some points above, I have some points below, right? So see, points above, points below, maybe some points on it. But generally this red line represents best fit line, or so best fit line like this, short. Because this gives you the trend line of your force versus X data. All right, any questions?
Yeah, when you say,
go ahead.
How do we turn in the lab?
You turn in the lab by doing your work on a piece of paper, taking a picture of that, converting to PDF and uploading on Canvas. I'm gonna change that lab 1 into an assignment module where you can actually submit.
Okay.
Go ahead, Jenny, you had a question?
yeah, so when it says K is spring constant, when you say spring, you're talking about the spring in your example, right?
Yes. It's
Okay,
like it's information about the property of the spring. So let's say, for example, when you have a spring that has a K of 10 compared to spring that has a K of 100, this tells you that, for example, this spring that has K over 100, right, is 10 times stiffer. And let's say if K is, for example, is 1, that means it's a very loose spring. That means this K is actually information about the property of the spring itself. Yeah.
Okay, thank you.
Sure.
Can you scroll up just a little bit so we can see the previous stuff?
All right, guys. So remember, this will be available on Canvas. This recording going to be available later on. But right now, I'm trying to get everything done so then we can finish it. But so this is what I have right now for that. All right. So now the idea here is this: if I'm taking force versus position and I'm plotting them like that, look at this equation again. That means if I go and look at how then, if F is Y and X is X, then K is nothing but M. What is this M over there in that equation, Y equals MX?
Slope.
A slope?
Slope, yeah.
Exactly, that's the slope. That means one thing I can do here is choose 2 points on the line, and you're gonna circle those 2 points, and then you use those 2 points to find the slope, which will be rise over run. That means 2 points on that line, not your data points, because for example, if you use this data point, that's not on the line. So it's inaccurate to use the data points to calculate the slope. Any 2 points on the line, rise over run, gives you the slope. But since the equation, the way this works, it tells you that M, the slope, is then gonna be exactly equal to your average spring constant K. Because remember, these are the averages, everything, right? That means finding the slope of the best fit line gives you directly your spring constant K. Okay. Again, all of this in the handout as well, but you know, remember, you can go back and watch this again later on. If you have questions, you can email me about that. But the data that you have, force versus position, will be plotted, and then you have a best fit line. Slope of that best fit line is then your spring constant K. But obviously we're not done. We still need this guy, uncertainty in K. So we need to find that. All right, so let's see how we can find uncertainty. Well, the way we find uncertainty is like this. If you look at the data table that I have for, for this particular assignment, then you will see that next to the force in the data table, it says uncertainty in the force. And then you are given uncertainty in the force. So let's say 0.5, 0.5, 0.5, and something like that. That means every value of the force that is given to you comes with uncertainty. Same thing, there's also uncertainty in the measurements of X. And there are sigma X for every data point that you have. Which means to find the uncertainty in K, we actually have to use those uncertainties in force and in position in your data set to get sigma K. All right, so the way we do is this. We say that, okay, so for example, look at this data point, right? So this data point, that data point is some force and some position that we plotted. But then the table tells us that technically force has uncertainty. So this could have been plus uncertainty in force and minus uncertainty in force. Same way it could have been plus uncertainty in X and minus uncertainty in X. That means all of those data points comes with plus minus the uncertainties in X, and let's say plus minus uncertainties in Y. That means in a force. Okay, so that's what we do with those, like looks like a cross. It's actually plus minus the uncertainties of your measurements of the force and the position. Now, what we need to do after this, after we get those, you need two more lines. Those two more lines, one is called a maximum line. The maximum line goes like this. This line has to go above all of your data points. So this is the maximum line. Remember, the red one is the best fit line. So then this is the maximum line. And then you're also going to have a minimum line. Minimum line goes below all of your data points. So basically something like that. Because the idea of those maximum and minimum is very similar to the, remember that the graph that I showed you, there's this distribution like that, which technically gives you the spread. Same thing is here. What we're saying here is that, for example, this is the spread for your data set. All right, this is the spread of your data set, which means, generally speaking, uncertainty in K is equal to the spread divided by 2. That's how we're going to find the uncertainty in K, spread divided by 2. But you still need to know, let's say, how do we find the spread? Well, it's not as difficult as well, because spread is going to be finding the slope of the maximum line, then subtracting from this slope of the minimum line. That means you have those maximum and minimum lines, find the slope of each of those two lines, and then spread is their difference. And then spread divided by 2 is then the uncertainty in K. That means what we have here is this then. The slope of the best fit line is used to find the average K. Then the slopes of the maximum and minimum line is used to find uncertainty in K. That means you find the spread by difference of the slopes of the maximum and minimum, and then that value divided by 2 is your uncertainty in K. Then you can come and tell me, okay, so here's my value of the K in terms of its average and uncertainty.
But how exactly will we take the slope of the maximum and minimum lines?
Just like you did for the best fit line. Just take 2 points. Here's 1 point, here's another point. Find the X and Y for that point. Find the X and Y for the second point. And then remember, slope is Y2 minus Y1 over X2 minus X1. Any 2 points on each line will give you the slope. So then again, randomly, maybe you go and choose another 2 points on the minimum line and use those to find the slope of the minimum line.
So if we're doing this by hand, because I know if you do it with like a graphing utility, it's easier, but with hand.
Everything is done by hand for lab 1.
Okay,
Yes.
so we're gonna have to like add the uncertainty on the points that are already on the line of best fit, and
Exactly.
okay.
That means
Right.
you have to do that. So also let me kind of point this out. So there's a graphing paper, and the graphing paper, let's say this big, right? For example, please don't then use this graphing paper to give me a graph this small. Because I've seen students do that. So they use the entire graphing paper, but then they give me a graph like this, right? So it's going to be very difficult for you to do everything accurately and for me to actually understand what you're doing. So what you do here is put a title here and then use a ruler to draw this X and Y axis that uses the entire page, right? And then you do your data points for, this is data points for F and X. Then you use the ruler to draw the best fit line. Then you do your uncertainties, let's say, right? And I'm just, you have to do that. You have to do them accurately. I'm just basically drawing them quickly. And then you draw those maximum and minimum lines. Then find the slope of each of those 3 lines by using 2 points on each line.
How do you get the maximum and minimum line again?
Just make sure that they above all of your data points. So basically they go above, you can see, right? They go above all of your data points.
But should they go on like the highest one and the lowest one, or just like slightly above and below that?
Yeah, so basically you can think of it like this. Maximum should be steeper than the best fit line, and the best fit line should be steeper than the minimum line. That means, see if I'm doing this, again, I call this a spread, right? See when, for example, let's say if I use this to represent my spread, then all of my data points is inside this spread, right? So that's why, for example, your graph cannot look like this. So let's say this is your graph and these are your data points. And let's say these are your, in terms of uncertainties. And let's say if this is your best fit line, don't do maximum like this because you're leaving out, some of your, uncertainties out. So the correct way would be to do like this. So everything is, below the maximum line. For the minimum, everything is above the minimum line, and so on and so forth.
Could the max line intersect some of the points?
It can, but maybe like the tip of them, but not necessarily go like this. So, but obviously you can do it so that it's above all of them.
And do all the lines have to start from the origin?
Not necessarily. Not necessarily.
Okay.
All right. Any questions? All right, guys. So this took me a little bit longer to cover. All right. So what I'm going to do here is this. So there is basically we're about 3:15 right now. So pretty much we're run out of time. So I'm going to give you the recitations and, I'm going to basically, it's already, I think, open, the recitations right now. So if you want, because, as I said, in my syllabus, I have from 1 to 3. So, and I'm going to open the breakout sessions and have you guys, I'm going to give you, let's say, about 30 minutes today, because we're a little bit, ahead, behind with everything. So I'm going to give you about 30 minutes. And if you want to stick around and work in the breakout session in your group, right, 30 minutes to spend to work on those recitations, go for it. Okay. But let's say I'm not going to hold it against you if you decide to leave, because again, my class time that I'm giving you is from 1 to 3. So this is kind of like beyond that time. But, I want you guys to still work on the, recitations, together. So let's do then this. I'm going to randomly, okay, all these groups are random. So I'm going to, have you work in maybe in groups of 6 or 7, like let's say 5 or 6. Recitation is already on Canvas. If you go down, scroll down, you see recitation, you should be able to see recitation 1. Okay, so you open the recitation 1 and just again, together in groups of 5 or 6, just try to solve as many problems as you can. Again, I'm gonna give you this time about 30 minutes. And usually on average, I'm gonna, in other days you will be getting maybe like, let's say 45 minutes. So 30 minutes today. So go ahead and start working on it. And if you finish, you finish, you submit. If you don't finish, you have until tomorrow midnight to submit that. I think there are like 5 or 6 problems and all dealing with vectors. And you should have basically no problem working on that. All right, so you should get an invitation to join a breakout session. So go ahead and join them and basically have 30 minutes to work on those problems.
Professor, I had a question.
Go ahead.
I accidentally missed the class on Monday. What can you describe, like what happened?
Like you didn't get dropped.
Yeah, I know. That's why I'm glad I didn't
about
get dropped. But like, what is, like, do I need to like, how can I like make up what I missed if I can do that?
Well, we haven't had any assignment yet, so this is our first assignment.
Oh, okay. And then, like, was there like a lecture on Monday?
Yes, there was a class. You always have a class Monday, Wednesdays.
But you didn't go over anything really?
I did.
Okay, and it's just on Canvas?
Yes.
All right, thanks.
Sure.
Okay, if we have to leave, we can leave though, right? We don't have to do this. Okay, all right. Thank you.
Yeah, no problem. You guys have questions? Because you should be getting an invitation to join the groups.
And for the lab, it's already, we download and print the handouts.
Yes. And then
We
there are,
only do lab 1, right?
yeah, the lab 1, and there are 9 exercises plus the graphing exercise. So basically 10 exercises that you need to do and submit.
Okay. And lab 2 will be for next Wednesday.
That's for next Wednesday, yes.
And if we have to leave, do we just do that by ourselves, the work, or do we? Okay, thank you.
Sure.